All right, so we're gonna now talk about how we want to interpret some of this model output that we previously saw. So in particular, we want to have an interpretation of the fitted intercept as well as the fitted slope. And so going back to page 4 where we fit or where we have our scatter plot with our fitted regression line, and we have our estimate for the intercept, which is negative 642.8. So remember, graphically, that is the value of y, which is run scored, when this line crosses over the y-axis. And so, in other words, when this line crosses over the y-axis, that's when x is 0. And so when that happens, if you would extend this line way, way down to when batting average is 0, it would cross over this y-axis at negative 642.8. And so we want to make that as interpretable as possible. And so let's go ahead and just rewrite our fitted regression equation just so we have that down. And so instead of saying things like, okay, well, when it crosses over the y-axis, this is what we would expect the number of runs to be, or something kind of weird like that, we want to put this as much in context as we possibly can. And so our estimate of beta 0, beta hat 0 is negative 642.8. So that's our estimated intercept based on the data that we collected. And so when we put this in context, instead of saying when x is 0, we just want to say what our actual predictor variable is. And so when batting average is 0%, then it's not necessarily what a particular point is going to be. It's more about kind of what's happening here on average. And so we would expect the average runs scored to be negative 642.8 runs. Okay, and so obviously that kind of doesn't really make sense. So we're going to jump down to this question about when we should interpret beta hat not. And we should really just interpret this when 0 is in the range of x values in our data set. So really not here, right? Because if you look at the scatter plot, 0 is somewhere way, way, way over here. It's way outside the range of x values. And so we shouldn't really be interpreting the intercept. And so since 0 is outside the range of x values here, interpreting the intercept is extrapolation. All right, so we really don't want to use our model to predict anything outside of like 23 to 28 or 29-ish in this example. And so we don't want to use it to predict the number of runs scored for a team with a batting average of 50%, because that's way outside on the right. We also don't want to use it to predict runs scored when the batting average is 0%, because that's also extrapolation. Neither of those are really in the range of our data. And so just so we kind of have a general interpretation for the intercept, I'm going to kind of try to put stuff in brackets that you would change for a particular problem. And so when x is 0, and then whatever the units of x are, then the intercept is really what we expect y to be on average. So we expect the average response, or the average y, and so that you would also put that in context, to be whatever our fitted intercept is from our table of output, and then units of y. All right, so in most problems, I guess most but not all problems, we're actually more interested in the slope because the slope is what tells us kind of a little bit more about the relationship between runs scored and batting average. And sometimes the intercept is completely irrelevant, like it is in this example, where it doesn't even make sense to interpret. And so remember, I guess from algebra or some other class, that the slope is just a measure for how much y either goes up or down for a 1 unit increase in x. And so again, we want to make that as interpretable as possible. We don't just want to say kind of the slope is this, because someone maybe not familiar with algebra wouldn't really know what that means. And so in this particular case, our fitted slope is 52.42. And so that just means for a 1 unit, or in this case, since units are percent, so for a 1% increase in batting average, so for example, if x kind of goes up from 24 to 25, what would we expect on average again to happen to runs scored? Well, we could tell from the graph that on average we would expect the runs scored to increase, and the slope tells us exactly by how much. And so if the slope were negative, then we would be expecting our response to decrease for a 1 unit increase in x. And so for a 1% increase in batting average, we expect the average number of runs scored, which is our response, to increase by 52.42 runs. In general, we're interpreting this like for a whatever the units of x are, increase in x. We expect our average response y to either decrease if that slope is negative, increase if that slope is positive, by whatever our fitted output tells us the slope is, and then units of y. So we're writing these general interpretations really specifically, mainly because they're going to kind of help us once we get to more complicated models. And so we're really going to use these as kind of our building blocks for when we say add in more predictors, or add in categorical predictors, or change our response so that it's categorical. And so we're kind of setting these up as a base, kind of in this simple linear regression case. Just to kind of note that when we're interpreting our slope, we really don't want to say anything causative. And so the reason for that is that almost all of the examples that we're going to use in this class come from observational studies. And so if you remember from Stat 113, in an observational study, there's no real manipulation of the predictor variable at all. And so therefore in these observational studies, we can't really infer causative effects, whereas in experiments, we can infer causation. But like this baseball example, we didn't really manipulate anything, and so it's just an observational study. And so we want to be careful not to say something So, for example, cannot say something like a 1% increase in batting average um, causes a team's number of wins to increase by 52.42 runs. A lot of times that's what we want to say because that's a lot stronger of a conclusion, and I think a lot of times it'd be nice if we could say this, but because the study is observational, we can't really make an interpretation like this. And so that's why we're being so careful with our wording back on our slope interpretation, not using any real causative language that might mislead someone into thinking that this is a causative effect when we can't really say that without some other outside evidence. Okay, and so next you'll kind of get some practice with this, both outside of R in this first handout and then with R to kind of fit the simple linear regression model. And then after that, we will move on to talking about this epsilon term, which we've mostly ignored so far, and talk a little bit about what the model error is and then what kind of assumptions we're making when we fit this model.